Pleasure to meet you. So I'm going to tell you about this aito.ai, which is a pretty unique combination of of AI technology and database technology, and I would actually say that it is pretty unique and interesting case even in the kind of world scale. But first of all, I would like to introduce myself. So I'm Antti Rauhala. Uh, this aito.ai idea it got its kind of foundation during my consultation years. So I have been in data science consultation for quite long, so maybe 7-8 years already. And I faced a lot of problems, and these problems partly inspired me to create this solution. So together with Kai and Vesku, we started Aito last year, something like December, and we created the company something like half a year ago, and we have been growing quite rapidly, as you might see. So we are now 8 person. But to the actual topic, so uh, I think the best way to understand aito.ai is by understanding kind of its problem setting, what inspired it. And to understand the problem setting, I would like to raise this question of what the world is actually missing around AI. And in here, well, let's state the obvious. So AI excitement and this anxiety, all this hype, it is really kind of driving people to act. So there's a lot of talk about AI, how it is changing the world. And obviously, there's just kind of enormous amount of applications around AI, just kind of millions, I would say. But at the same time, and this is kind of what I faced in my consultation years, is that well, this is kind of pretty typical case. So we have some kind of business case. Let's say we have some 10 million euro business, which is kind of medium sized in Finland. They may have some 10% margin. They may have, and we may be kind of looking for some few percentages of additional sales with some machine learning solution. And what we run into is that we actually are looking for benefit in the magnitude of 100,000 euro. But when we start to kind of plan the project, there's going to be handover from the development team to the data scientists. There's going to be a lot of data preparation, modeling, evaluation, iterations in here. And even further, there's going to be integration into the actual environment, getting all the data pipes running. And this actually can be really expensive steps. So it can be a lot of work to make, to integrate machine learning system in the process or some application. And as a result, there are actually tons of cases which look like this, which provide clear benefit, which makes sense on the benefit side. But when you add the kind of numbers together, you realize that return on investment just kind of justify the project. And I would claim that 90% of the cases are either like this or they are much worse than this, that they are actually much more expensive than the benefit of the AI solution. Obviously, there are also a lot of AI applications where you can have huge returns, but for most cases, the economics don't kind of allow them to happen. And now, obviously, the question is that could it change this kind of setting? But is it possible to make AI much cheaper to reduce the investment by somehow radically? Let's say 90%. And the basic premise is that if we would actually bring the cost down, what would happen is that there would be just tons of applications kind of coming from here, which would become sensible to, and even the kind of existing applications could be much more rewarding in here. And I think this could kind of open the door to democratization of AI, of getting AI to every service and every kind of feature. But regarding this kind of 10x AI system, in a sense, it should have certain qualities in order to work. So when we look at the process, most of the kind of work is in here, and the kind of 10x AI system, it should pretty much eliminate this kind of step entirely. So in a way or another. So obviously you need to have the data, you need to prepare data somehow, but with such system, you could maybe get the instant results instantly, a bit like with SQL, let's say, just kind of ask instantly the predictions or some kind of recommendation or anything you want from arbitrary queries and to get kind of any kinds of results. The second thing is that the API actually should be comprehensible in order to eliminate the first of all the handovers. So the handovers from development teams to some special experts can be pretty expensive. And the second thing is that just if you can kind of eliminate this step and get the results instead of some like weeks or months in some like milliseconds or tens of seconds for a specific problem, you can reduce the iteration time, and when you can reduce the iteration time, you can reduce the planning and work more agilely and be more productive there. And the third thing is that it should be pretty generic, so it should actually be possible to apply this kind of system for most of the problems. And these are obviously kind of lot of very kind of strict constraints. And now obviously kind of question is this kind of system even possible to do? Is it possible to do this kind of 10x AI? Now I would like to kind of describe how Aito works, and I would again like to describe how it kind of functions by describing the problems that inspired Aito as a solution. So, well, the first problem is what I faced some like long time ago, and it was about creating this content-based personalization for basically aggregated news. So I had tons of articles. There was database having the articles, and the backend was kind of filtering the articles based on the view in order to get the results. And what we were kind of asked to do was to provide this kind of AI to actually sort the articles what the database was going to give us. And the first problem is that how you actually make this work together. Now, the second and third problem, they're actually caused by the kind of first problem. So this is one architecture. So we have database in here, we have the backend in here, we have microservice in here. But in here, we run easily into problems if we have a lot of content with long IDs. So this actually can be something like 10 kilobytes of data to move from database to server to AI, and it can affect performance, and it can kind of congest the network. And it can be even worse. So in some cases, the candidate list could be something like megabytes. And once you run into that limit, the performance is going to kind of, it is the end of performance, it is the end of responsiveness. You cannot make the system work in any kind of business domain. And this is a huge problem. And the other problem, which is more practical, is that if you have content-based personalization in here, and you have content in here, you end up duplicating the content, and you need to make all the integrations to synchronize the content in here, and you're going to have this in different states. And this is going to be a source of additional work, and it's actually pretty expensive architecture to have. And well, what we did was that we actually integrated the database and machine learning really tightly. So database, or the Lucene, what we used at the time, it has direct interfaces for sorting functionality. So what we did was that we put the personalization model as a sorting interface, and suddenly they integrated seamlessly. They started to kind of really operate without kind of any kind of problems together. The problem of network, it completely disappeared. So the machine learning can basically use the memory of the database because it is in the same process. And also all these kind of synchronization problems, they simply cease to exist because, well, they are using the same data, which is kind of interesting. So you can actually solve a lot of practical problems by integrating database with AI. The problem number two was that, well, let's consider situations that we have like some, let's say, media side, and there are a lot of people coming there, but a lot of these people are basically cookies, and they are some like one-time visitors. And if you would like to personalize the model, you may have some like 1 million users, but most of these users don't have a lot of data, and you don't actually have a lot of data at all, and you don't want to maintain some like 1 million personalization models. It is not just feasible. You can't do it. But now the kind of big question is that what if when you have this kind of user coming in, some kind of setting coming in, what if you could actually create the model for the specific user in milliseconds? Suddenly, a lot of these practical problems, they just disappear away. You have user there, you create a model, you use the model to create the personalized users. But is it even possible to? Can you train models in milliseconds? And now it occurs that if you have a database which indexes are kind of optimized in a way that it is fast to calculate statistics out of there, you can have absolutely massive improvement in the training speed. This is just a lot of zeros of improvement. And when you have this kind of really specific case, you can also kind of narrow the problem setting. And the kind of fun thing is that you can actually solve this problem by integrating the database and the machine learning functionality even more tightly. The problem number 3 is kind of related. So let's say you have settings that you have created model, but you have actually a lot of data to train. So you may have, let's say, 250,000 items what you want to train, and you have maybe 500,000 features there. 500,000 sparse features, but still like crazy amounts of data. If you multiply them and try to go row by row, it is not going to something like work. It may take hours to provide one result. But the funny thing in here is that you can actually solve this problem just by scoring from the indexes. So you integrate the database with scoring. In the scoring functionality, because the features are the indexes are organized by feature, you can just kind of subselect some interesting set of features, maybe 100 features. The features may be sparse; they may be just some like hundreds of this kind of true states, even in this kind of huge data frames, and it becomes actually pretty fast to score it. It may be some like milliseconds, so it can be even faster than training. And it is also interesting because now we have 3 problems that can be solved by integrating database with the AI more tightly. The 4th problem is actually a bit different. So the thing is that we can obviously provide some like predictions and we can do some other functionality there. But could we actually kind of provide very wide set of different kind of intelligent functionality, a kind of portfolio of smart functionality somehow easily from the same kind of setting? So what Aito does is that we provide some kind of analytics diagnostics. We provide smart sales functionality, we provide predicting, we provide matching, and we provide recommending. And this is actually kind of design problem because just kind of implementing each functionality as alone can be a lot of work and a lot of code to maintain. And in here, our solution was that we actually took the kind of textbook base in mathematics and we derived all these kind of different functionalities, these different smart functions from the same kind of mathematical foundation. And what we did was that because they were based on the same mathematical foundation and they shared a lot of functionality, we just moved the shared functionality in this kind of representation layer, which contains both the data and the way how data is represented, but also abilities to kind of get statistics and see how things relate and all these kind of statistical utilities in here. And it enabled us to have thin statistical reasoning layer and kind of fat representation layer where all the kind of shared functionality is located. And it is kind of nice design just and it makes things much easier. Now the problem number 5 is that well we don't want to create this kind of deep learning black boxes which provides features results what you can't explain. We want to provide kind of comprehensible and sensible results. What are sensible for the users? And in here, our solution was that well, this kind of problem has already been kind of solved at this point. So one of the things is that when we have this kind of Bayesian approach, the Bayesian approach actually provides this kind of probability drifts. For example, we may get the information that when we have some old customer, the old customer is probably going to buy just overall buy things like twice as more likely, and they're probably going to prefer these kind of products. Let's say 30% or likely, but they are not going to buy this kind of thing with 10% lower likelihood. And this is this kind of twice as likely, half of as likely, and so forth. It is very comprehensible. It's very understandable for humans, and as such, it supported this goal. Another thing is that if we want to provide some highlights, let's say you are looking for some laptop and we know that you like, let's say, Apple products a lot, we could like highlight the Apple and maybe provide some explanation that you like Apple in here. But how to do it, and it is actually very easy when you have database which contains all the original data. So you have the title and it's very easy to find this Apple feature from there and highlight that this is what you were looking for. And the third thing is that this representation layer, it can be kind of engineered in a way that it actually kind of has the graph. So if we do some kind of transformations there, we create higher level features. We can make it transparent in the sense that all the kind of features are actually explained by the original features what we put there. So this is kind of design decisions how we kind of attack this problem. Another thing is that well, we can make this either non-narrow. So instead of being a pipe where you can put some input there and get output there, you can pretty much ask any kind of problems there. We can make it fast, we make it scaling, we can make it comprehensible, and we can make it generic in the sense that it actually kind of provides this portfolio of smart functionality. But one question is that can we actually make it to provide us good predictions? So the basic problem in here is that if you have some tens of milliseconds of time in here, you're not going to train some random forest or some kind of fancy Ansible model in here. Even if you optimize it really kind of extremely. And the solution in here was just that, well, reason was right, and the fact of the matter is that you don't need to make better models if you can make better representations. And if you actually create a representation learning technique and you transform the representation to higher level representation, which kind of optimize the minimum description length, you can not just kind of improve this kind of Bayesian approach results, but you can actually improve the speed. Because when you have higher level features, you need less features, and with less features, you need less computation, which is kind of interesting. So we tested this in one customer project, and it was actually working very nicely with a lot of data and with pretty large scale. And the problem number 7 is that also it isn't yet implemented actually in AITO yet. But the problem number 7 is that well, this is a problem which I have faced quite a lot of times. So if we have Bob Smith, so we have some invoices with some text in here, and in this invoice text we have like invoice Bob Smith, and we can see the browser is Bob Smith in here, and we can see that the invoice is going to change Gilliams, and the browser is going to change Gilliams in here. The problem here is that if we have invoiced Matti Meikäläinen, and we have never seen Matti Meikäläinen before, absolutely never seen this kind of features. A lot of machine learning algorithms are going to just fail because they are not going to can't recognize, they don't have history, so they can't make any kind of inference from Matti Meikäläinen to the process of Matti Meikäläinen, even if it is in the if you can find it in the table. And this problem was actually solved by adding more semantics into the features, so the features became less black boxes. And also another thing was this analogies frame. So one idea is that with analogies you can have this kind of super features, or like let's say bird. And you could have this kind of really specific features like, let's say, duck or swallow or swan, which inherit from the kind of super feature. And the super feature gets its kind of statistical properties from all the kind of these kind of specific features which implemented. And now we can reason from bird, let's say, some whatever it is, hawk, even if we know nothing about hawks, as long we know it is birds, so we can make this kind of prior assumptions that maybe it behaves like all the other birds, and we can make inference based on that. And another thing is that we can actually have this kind of super relations also. So if we have relation from Bob to Bob and John to John, we can have also this kind of super relation of X to X, which from which all these kind of specific relations inherit. And if we can see that over all this kind of X to X relationship, there is actually very, very strong statistical pattern of if you have this in here, you will have this in here. This actually enables us to, that when we find this kind of Matti to Matti relation, to make prior assumption that Matti and Matti are actually really strongly statistically connected. And it allows us to kind of make inference without having any data of this feature. And if we get kind of information that they are not actually connected at all, it is going to converge to that result. But also it is interesting in the sense that it actually unifies statistical reasoning and searching. Another thing is that it provides this kind of inheritance kind of structure, and it provides priors in case where we have no data. And it actually allows us to have this kind of variable-like reasoning in AITO. So if previous topic is X, we may kind of infer that maybe the next topic is also X. So maybe there's some kind of continuity. And in a way, this is AITO. So the AITO was inspired by this kind of unconventional, but actually pretty common problems. And as such, it is. It has the kind of statistical reasoning layer, it has representation learning layer, it has this kind of the semantic representation there, and it has really tight coupling and really tight integration between database and AI levels. And from outside perspective, it actually kind of looks like a database or search engine. So how you use AITO is that you pretty much take it into use like Elasticsearch. So you need to plug in data. There are these tables which are cross-linked. You can make inference from through the links. So if you have impression table there and this pointing to users table and product table, it can kind of use the information in this user and product table to give you results. But after you have plugged it in, you basically start kind of getting instant results, and you can integrate AI like you can integrate SQL queries. So it can become straightforward. And in the easiest case, it can be just hours to kind of get some kind of functional to work if you have the data inside AITO. Aito. This is what the queries look like. So in here we have the basic structure actually copied from SQL. So we have from where select. We have also offset and these order by and all these other things. But and we have the basic kind of query syntax. So this is JSON, and we have basic query syntax copied actually from Mongo. But in here we say that we are looking at the impression table. We state knowns. So we know that the user is like this and query is like cheap laptop. And we can ask Aito to recommend some product to maximize this click likelihood in here. And then we can select, do some selection. And in the selection, we can ask for probability, but we can also ask for explanation for the selection. So what relations, for example, in here related to the different product qualities. And we can also ask for smart highlights there. So it's going to highlight the things which were way important for you. So if you were looking for a cheap laptop, maybe it's going to highlight the price. And as such, it actually has a lot of qualities of this kind of imagery 10x AI. So it can provide instant results to arbitrary queries, very much like SQL, and it is as easy to integrate as SQL queries. Another thing is that we have the data preparation here. It has comprehensible API, and you can integrate it like Elasticsearch. And the expectation is that normal data science or normal developer teams could actually kind of use it, and there wouldn't be need for these handovers and a lot of planning. And the third thing is that it's actually kind of generic because it actually supports this kind of portfolio of smart functionality. And this was actually it. So this is kind of Aito in Consel. Thank you. We are actually recruiting. So if you are interested of joining Aito, just go to this aito.ai website and look what's available.
So I want to ask you. So is it like you have an AI situated in a database environment? Is it like a supervised learning or unsupervised learning that they are doing? So if it's supervised learning, where does the training set come from?
Well, basically, they are both. Well, this kind of statistical reasoning layer is basically supervised learning, but it is supervised learning in the sense that we have the kind of traditional bag of features to some let's say classification problem, but we also have bag of features setting, and also this country variable setting for recommendations. We actually I have implemented this representation learning before. And we had some kind of trials in here also, and we have kind of prepared it to be integrated into Aito. But the representation learning is obviously kind of unsupervised learning. So, but if you ask that where the data comes from, the actual tables, what you have in the database are the data. So the table as such is used as the train data. So if you have, let's say, impression data of, let's say, 1 million rows, it is going to use those 1 million rows to construct the models. One of the things in Aito and its kind of unconventional kind of nature of Aito is that it kind of it a bit defies the kind of traditional supervised learning, unsupervised learning kind of categorization. And I think Aito is actually kind of more closer to what we can see in some classical in classic AI. So we have this knowledge representation systems where we have the knowledge representation layer and where we have this kind of reasoning layer. For example, Prolog is one example. So you have the data there, and you may have some this kind of make some kind of reasoning based on data in the reasoning layer. And we have models there, and I think the kind of moment, this kind of immediate spot where we create a model in some like milliseconds or tens of milliseconds to fit certain kind of problem setting, that is very much like unsupervised learning. So we are looking at these million rows in the table. We have some clearly defined problem setting by having this kind of parameters there. We have clearly defined problem setting of what we try to kind of predict or recommend. And it is kind of unsupervised setting in its kind of entirely, but these are like ad hoc models. They are used only once and then throw away. and it kind of disappears from there. So you actually never see the models there. You can just kind of see the query which goes in and results that go out. But regarding scaling, we have been able to make the three-variable examination, which is the kind of most expensive operation to scale it to something like 1 million entries. And it is kind of nice, but it's not actually, it is not yet something like super sufficient for all situations. So if you have some service which have like tens of thousands of users already and they generate a lot of data, active user, you easily run into data frames of some like tens of millions or hundreds of millions impressions. But I think this kind of basic inference like prediction settings, they are definitely faster, and I think either can actually manage most of these kind of traditional machine learning settings kind of nicely. So it is not kind of strongest machine learning. So I think the results are somewhere in the magnitude of naive Bayes. So it is Bayes and it is pretty naive inside. But we are not trying to kind of provide the best machine learning system available, but we are trying to kind of make it as easy and fast to use as possible.
Yes, thank you for the presentation. Quite interesting. I think it was your problem 6 where you mentioned that are the results useful? Would you have any concrete examples of how you measure the quality of your recommendations, and do you have any recommendations of how to do the measurement?
Well, we have internal test beds inside the AITO sort of project where we do this train test splits evaluations, and we are using several metrics there. So one is traditional accuracy, obviously, but another thing is that we try to kind of provide probabilities. Also, we are not always something like super successful there. So we are using this information theoretic like log likelihood metric in order to measure that. Or actually, well, there's some like a family of these very similar kind of metrics. So it is basically the same metric as the likelihood, maximum likelihood, and the variation what we are using is like geometric mean of the likelihood, which is basically log likelihood. So yeah, and we have few customer data sets what we have been using to optimize it, and we have also some public data sets like DNA splice, and it is kind of showing that AITO is working a bit like Bayes basically. So it is not the best kind of system. We want to at some point put more focus on improving the results and making the quality better. But at this point, our focus is just making it easy to use and getting these kind of good enough results easily.
So Eki from AI Reactive, thanks for interesting presentation. And I have a question that, can you disclose any real-world use cases that you have been using this for, and what kind of accuracy results you have received if you have been using this in real-world situation, and if you can disclose those?
Well, there are few examples. So one is well, we actually the Helsinki this project is in productization and in the train test bed. So this is kind of a funny machine learning problem, but because we had very little data. So the Helsinki problem is that they have like IKEA kitchens, and they need to find this kind of surfaces to the IKEA kitchen products. So what they wanted to have is this kind of automation for creating a shopping basket for certain IKEA kitchen. And how this system worked was that it would take IKEA product and it would find the matching Helsinki product, or it would, let's say that this is, let's say it is a lamp. There's no Helsinki surface for this kind of things, this kind of silly setting. And we had like 54, or was it 55 samples? And I evaluated with something like 45 training samples and 10 sort of test samples. I didn't do cross-validation because it's a lot of work, or it was more work, but it guesses 7 out of 10 of the kind of cases easily. But it is a bit silly case because there's so little data. But it is a case where either kind of shines because it is not some like super complex problem. So you have like this height and you have width and you have some other properties, and there are like really strong patterns there which are very easy to kind of detect, and it is kind of easy problem to make work, and we got actually pretty nice results out of there, and I think in this kind of case actually Aito shines because it was easy to make the demo, so it took 7 days to make this kind of first proof concept of the shopping basket automation. It is easy problem, and this kind of pretty simplistic system can actually provide pretty stellar results in that kind of problem space. There's also been few other cases, Skinneri Labs. One was this Tidy who were doing conversion analytics. So in Aito, the problem was basically that we have the conversion of whether people can buy or whether they not buy, and we have impression data, and the question was that what kind of things actually make people buy and what kind of things make kind of also Aito's kind of natural turf, because Aito is all about kind of finding the statistical relationship as fast as possible, and the entire sort of underlying system has been optimized for that purpose. So it is pretty kind of easy to kind of find this kind of relationship and also ask this relationship in certain kind of scenarios.
Yeah, you mentioned Prolog and this kind of rule-based systems. It sounds like a forward reasoning rule-based system, that kind of you reason in the forward direction probabilistically some result. It's like sounds like if this Matti Meikäläinen thing accepts to pay the invoice, then you kind of have a maybe supervised learning in the sense that you can strengthen the assumption that okay, these are good rules because it works. But how do you kind of come up with new rules or build the rule base? Because it's kind of now Prolog-like of there are facts and rules in the same base, and you reason. Have you looked at the inductive logic programming or kind of a system to kind of keep up a rule base that's good?
The thing is that there's Aito is kind of in interesting kind of spot where it has a lot of kind of features and a lot of appearances from traditional machine learning, but it also has some of the kind of appearances of this kind of classic AI systems. And in classic AI systems, well, the difference between this kind of machine learning and classic AI systems is that in machine learning you have these relationships from A to B, which are typically kind of soft and weak, while in this kind of classic AI you have this kind of really strict relationship. So if A, it must B must kind of occur. And because in machine learning, because you have so kind of weak relationships and the data structure, there isn't kind of recursion, there isn't kind of paths what you could kind of look for. It doesn't make a lot of sense to kind of do this kind of forward planning, because you can take a lot of steps forward with weak relationships without kind of making everything into kind of mess, because just everything becomes possible. But I think in Aito and in a lot of cases it is actually possible. There are a lot of really strong rules in businesses, for example, like that if you actually have invoice going to Matti Meikäläinen, the likelihood is that the processor is going to be Matti Meikäläinen, except if he's on vacation or something like that. But it is almost like really strict rule. And if you would have this kind of really strict rules, what you mine from the data, and because we have this table structure where you have links, this table structure with links, it actually kind of creates a tree in the sense that you can have actually recursion back to the same table. So you can have this messages table, which links back to the kind of previous message. And you could have this kind of scenarios that if you say this kind of thing, what the person says, and if the person says this thing, maybe what he maybe says next. And in theory, it actually would be possible to make searches in that space, and it would be possible to do the kind of things what kind of Prolog kind of does. And it has a lot to do with the representation. So one of the ideas is that if you have simple representation, you are going to have a simple problem, and you're going to have simple solutions in a way. So if you have a stupid problem, you're going to have stupid solutions. And I think this kind of applies to traditional supervised learning settings, because you don't have recursion there. You don't have, it is flat structure. It is not even possible to span trees there. It lacks quite a lot of the kind of this kind of power of expressiveness what you see in knowledge representation systems. And it's kind of interesting, because in knowledge representation systems you have things like Prolog, which is Turing complete, which is like super strong and super powerful. And in machine learning systems you have something like neural networks, which is like really kind of flat and very kind of unstructured, and which is kind of less internally. And there's like huge gap between the kind of machine learning and the classic AI. And we are kind of trying to fit somewhere there, hopefully.